Hello, everyone. I'm Arnav Ozdemir, a first-year PhD student studying material science and engineering at Penn State University, and I'm going to be discussing dielectric conduction mechanisms today. So as a general base knowledge, a dielectric is a material that is able to sort of conduct an electric force without actually conducting the electrons, i.e. it's an insulating material. So you can kind of think of this where if we have a chunk of material here with some sort of electrode on top, so let's take aluminum nitride for an example, and then we have our electrode, and an electrode on the bottom. Basically, if we apply a field from our, let's say, our top electrode, applying a field, then this field can actually be transmitted via a congregation of charges on either side, which will obviously depend on the way you're pulling your material. And while this material is typically for a dielectric is insulating, that we still actually do observe electrons that can get transmitted through this, whether it be through tunneling, hopping, or other mechanisms, which I'll be discussing today. Now, these mechanisms can actually be broken down into two different categories. So we have our first category, which is bulk limited conduction mechanisms. So this means that the conduction, this means that our conduction is dominated by whatever is going on in the material itself. So in our bulk here. Alternatively, we also will have electrode limited conduction. And more specifically, this is limited by whatever is occurring at the electrode-dielectric interface. And these will obviously be dominated by different mechanisms. And so whatever is limiting the conduction is going to be what controls it ultimately. Similar to a reaction, whatever is reacting slowest is what's going to drive the rate of the reaction. You can think of it that way. And so first off, we can look at our bulk limited conduction mechanisms. And there are a variety of them. So some of the bulk limited conduction mechanisms include Poole-Frankel, hopping conduction, ohmic conduction, space charge limited, ionic conduction, and grain boundary limited conduction. And so for this, what I'm going to be focusing on today is the Poole-Frankel conduction as well as space charge limited conduction, as these are what is more commonly observed, some of the more commonly observed mechanisms. And also I just happen to know a little bit more about them as they have become relevant to the research that I have been doing so far. So to start off, if we look at Poole-Frankel conduction, this conduction mechanism is characterized by electrons moving through an insulator, or the dielectric in this case, through a series of hops down intermediate trap states until it gets to the next electrode. Specifically intermediate trap states within the material. And these trap states could be things like vacancies. So if we take the aluminum nitride example, it could be nitrogen vacancies, among other various trap states based dependent on the defect chemistry within your material. And so sort of a visual schematic that we can look at for this is if we take this as our sort of dielectric, here we have our metal with our original electron. And then here we have our other metal electrode, or you can also have a semiconductor or other conducting sort of surface or bulk material here. But for our sake, we're going to just look at metal as well. And so we're specifically looking at, and I'm going to exaggerate this a bit more, we're specifically looking at how does this this electron right here, how does it end up on this side? Because you do actually get a finite amount of current. Let's take our aluminum nitride example again. For certain types of alloyed or doped aluminum nitride, you actually end up getting with around 10 to the, I want to say -12 picoamps of, or nanoamps of conduction through this material. Even though it's an insulating material, you should, in theory, expect 0. So Poole-Frankel conduction, the way this occurs, is in this sort of region here. In that region, you actually have a series of trap states. And what actually happens is that our material is going to, or not our material, our electron here, our lovely little electron, is going to hop into this state, and then sit here, and then hop again into this state, sit right there. All right, and then sorry about that. And then it'll hop one more time, or however many times, depending on the number of states. Obviously, in a bulk material, there's going to be quite a few defects just because we're working at an atomic scale with electrons. But you get the general gist. It's going to hop down until it reaches the metal, and thus you get conduction. So if we're looking at our diagram right now, we can actually define some important terms here visually. So here we can kind of define this sort of gap as our QT, or our hopping barrier. So this is basically the amount of energy that the electron needs to have in order to be able to hop into these, down through these trap states into our other metal electrode. And basically by fitting experimental data, we're able to extract the amount of energy that this actually is based on our data, which should relate to a certain defect state that we expect within our material. So if we're continuing off of this aluminum nitride example, for example, we can think about its defect chemistry and let's say nitrogen vacancy, which might sit at around 0.3 eV below the conduction band. And so if we end up getting hopping based on a 0.3 eV activation energy, then we can tell from that potentially we have electrons hopping through nitrogen vacancies down to the metal. And so we can mathematically relate this using this relation where we have J, which is our current density, equals Q, or a standard electronic charge, mu, our electron mobility, and sub C, which is the density of states in the conduction band, as well as E, our electric field applied, and then we have exponential here. In this, we have negative Q, and then we have this phi sub T term. So this together is our activation energy. And then we also have Q divided by, or QE divided by pi epsilon I, which is our relative permittivity, or more specifically, in this case, we're looking at the optical permittivity, as electrons are operating at frequencies where other contributions to dielectric constants, such as polarizability, space charge, or ionic contributions are basically phased out because we're operating so fast that only electrons are really able to keep up. And then also permittivity of free space. And then all of this is over Boltzmann constant times temperature. And so what we're able to do is you're able to measure a given material. So let's say we have our aluminum nitride, and then we have our electrode on top, and the electrode on the bottom, and we apply voltage. Some finite amount of voltage, V, and we measure the current that actually is flowing through. And you basically can get a plot, some set of data, where you have current versus voltage. And this plot alone won't actually be what we're using. Instead, if we want to, let's say, look at Poole-Frankel emission, we know that based on this mathematical relation, that if we were to actually instead plot a log of the current density over the field versus a log, or versus the square root of the field, and if we get a linear behavior with this, then that tells us that we have Poole-Frankel dominated conduction. And then from this, we can measure at multiple temperatures and use that to extract our activation energy. And that'll tell us this trap level. And so that'll tell us what trap states are actually dominating this conduction mechanism specifically. Some other potential conduction mechanisms that are similar to this is that we can have sort of a hopping conduction in which instead, interestingly enough, despite the name, instead of it sort of jumping out of these states because these electrons have excited with enough energy, instead the electrons can tunnel through to the next state. And so this is a quantum mechanical effect in which, due to electrons being a quantum particle, they're able to tunnel through potential barriers with a finite chance if given enough energy and depending on the height of the said barrier. And so that's another conduction mechanism that you can check for. Another potential conduction mechanism is the space charge limited conduction mechanism. And here, this is defined by a variety of laws in different regions, but as a general trend, if we look at the same plot where we are plotting, where we're measuring current and voltage, we can then plot instead. We can look at our log of our current and log of voltage. And here, if we are in a space charge conduction dominated region, we should expect a very specific type of behavior that is going to look like this, in which we have this linear region where we expect a slope of 1, which means that our current density is proportional with just V. And then at this point, it'll go up to a slope of 2, so that current density is proportional to V squared. And then it's going to jump up and then continue at a slope of 2. And so we're still going to be there. And then we call these 2 points, the trapping voltage, and then the trap filled limit voltage. So T sub V sub T FL, and then V sub TR. And so basically what we're doing is, so we have those traps, let's say, again, nitrogen vacancies and aluminum nitride. And then we're sending electrons through this material, and then electrons are getting trapped in those sites. And so now that there's electrons there, further electrons will then pass over these traps. So up until here, we have purely ohmic conduction. Here's where we start filling those traps. So think of like little marbles rolling down a board with a bunch of holes in it or pits in it. Slowly, marbles are going to slot into those pits, and then more marbles are going to roll over those and slot into further little pits. And then this jump up is when all those little trap states or all those little pits are filled up. And then now we have, again, another square region where all of our traps are filled. And so if you sort of see this type of behavior, then you can label it as space charge limited conduction. There are, of course, other ways and other factors that play into this. For example, in this case, the size of your sample is important. So if you have a sample that's thicker versus a sample that's thinner, the thicker one is just going to have more defects in it and have more trap states. And so you can also vary your thickness experimentally to see if this is something that you're observing, as you'll get more of an effect on it with thicker samples versus thinner samples. So these are some of our bulk limited mechanisms. So now let's also look at a electrode limited mechanism. And the one that we're going to be looking at, which is fairly common in these types of materials, is what is called Schottky emission. And so here we can draw a similar thing as to what we drew for this electrode limited. This is Schottky. All right, so here we have our metal. We have our dielectric once again. In this case, it doesn't really matter, but we can say ALM because why not? And then we have our other metal. We have this electron here. And now the way this is going to work is this is much more temperature dependent in the sense that basically we're thermally exciting these electrons up and over this potential barrier. And then it comes down here and goes off to do whatever it needs to do in that circle. But this is what it defines Schottky emission. Also, I think it is sometimes also referred to as thermoionic emission, hence why it, coming from the fact that these are thermally activated electrons being pushed over this energy barrier due to the heat of the system. And so this one has a slightly different equation that dictates it. So we have our current density J, and then what we call the effective Richardson constant of the material, and then that is times T squared or temperature squared, and then exponent of negative Q, and then phi B. And I guess this I should mention, similarly to the Poole-Frankel model, we could define sort of a potential barrier here of Q phi B, which is the energy required for it to hop over. And so that's what this term right here is. And then we have minus, and this part is going to look fairly similar. We have QE, or electric field, divided by, and this is important to note, we have 4 pi instead of just pi here, and then relative permittivity or optical permittivity more specifically, and then permittivity of free space. And then this is all divided by kBT. And so here we have a slightly different relation, as noticed specifically by this T squared. And so when you take your current voltage measurement, let's say you tried for Poole-Frankel and it's not fitting, and maybe you're suspecting it could be electrode limited. So one way to check that is to see if you have a linear relationship between the log of current density over temperature squared versus field to the 1/2 or root field. And you should get, again, some sort of linear slope. And then furthermore, you can measure this at different temperatures and calculate the intercepts and then extract your potential barrier from this as well as your effective Richardson constant. It's important to note here that the potential barrier specifically relates to the work functions of the metal electrode as well as your dielectric that you're conducting through. And specifically, it's going to be, you expect this potential barrier, as you are being limited by what's at that interface, you expect it to be the difference in the work functions of these two materials. And so in theory, another way to test that if you have an electrode limited conduction mechanism is to simply switch the electrodes and see if you have different behavior. Or another way that we could do this for, let's say, aluminum nitride or any other material is to look at it in 2 different directions. So if we have, again, our material, so our dielectric, and then this electrode, so we can either, when we're applying our voltage, we can do like plus and minus, I guess, maybe bad notation, but we can do this, or we can swap and do the inverse polarity so that now you're testing the other interface. And then if these 2 electrodes, let's say this one is platinum, pick a fun little color here, and then this one is tungsten. So now you're testing the interface between the dielectric, let's say aluminum nitride, and tungsten, in one case, you're testing that interface versus the dielectric and the platinum interface. And you should expect to see different behaviors based on this. So this is an easy way to check if you have an electrode limited conduction mechanism, since you should expect different slopes for this plot here, as that should be related to your activation energy or that energy barrier, which should result from the difference in the work functions. And platinum is going to have a different work function than, let's say, tungsten, which is going to have a different work function than potentially an oxide conductor that you could also use for an electrode base. So these are some of the different dielectric conduction mechanisms that we can look at. And these are useful to understand as they help us understand the defect chemistry that is at play within our materials. That's how I specifically use it for my research, as we're further trying to understand the defect chemistry of certain ferroelectric materials so that we can better understand fatigue mechanisms and such. And so this is a method that we can use to probe kind of what's there and what's contributing to the conduction, which can help us elucidate information about sort of what's contributing to that conduction mechanism, and thus specifically the defect chemistry and the defect structures that we have at play within our material. And we can do this at various states within our material at various points of, let's say, fatiguing, if we want to analyze how sort of like this evolves with the lifetime of the material, for example. And so these are just some of the things that you can do. And of course, there are many other conduction mechanisms in dielectrics, as I had previously mentioned.